Hi students, welcome to the 12th lecture in permutations and combinations. I hope you have watched the previous 11 lectures. So in this lecture we are going to discuss few more results related to combinations. So before looking into few more results related to combinations, let me recall what we have done in the first 11 lectures. So we have discussed about fundamental principle of counting, both multiplication and addition. In case of multiplication, a task is divided into two works, W1 and W2. In case of addition, a task can be performed in two formats, W1 or W2. Coming to multiplication, number of ways of completing the task is equal to number of ways of doing W1 times number of ways of doing W2. Coming to addition, number of ways of completing the task is equal to number of ways of doing W1 plus number of ways of doing W2. That means you have to remember these two. Whenever n comes, you have multiplication. Whenever r comes, you have addition. And we have defined factorials. And we have defined linear and circular permutations. And the number of linear permutations of n distinct objects taken r at a time is denoted by NPR, and NPR is equal to n times n minus 1 times n minus 2 so on up to n minus r plus 1, which is equal to n factorial upon n minus r factorial. So you should not read it as NPR, you have to read it as number of permutations of n distinct objects taken r at a time. Therefore, number of permutations of n distinct objects taken r at a time is equal to n factorial upon n minus r factorial. And we have few results related to NPR. NPR is equal to n minus 1, n times n minus 1 p r minus 1. We have given two proofs for this one. And next we have this result. NPR is equal to n minus 1 p r plus r times n minus 1 p r minus 1. So here r times n minus 1 p r minus 1 stands for number of permutations of n distinct objects taken r at a time, which always includes a particular object. N minus 1 p r stands for number of permutations of n distinct objects taken r at a time, which does not contain a particular object. And NPR stands for number of permutations of n distinct objects taken r at a time. Therefore, number of permutations is equal to total number of permutations in which an object is not there plus number of permutations in which a particular object is there. This is an important result. We will have a similar kind of result in combinations, which we are going to deal in this lecture. Next, when repetitions are allowed, then the number of permutations is going to be n raised to r. So when repetitions are not allowed, then the number of permutations is going to be NPR. Number of permutations of n objects, n distinct objects taken r at a time is going to be NPR. When repetitions are allowed, then the number of permutations is going to be n raised to r. Now, number of permutations in which at least one object is repeated is n raised to r minus NPR. N raised to r gives the total number of permutations where repetitions are allowed. NPR gives the number of permutations where repetitions are not allowed. Therefore, n raised to r minus NPR gives the total number of permutations in which at least one object is repeated or one element is repeated. Next, we have looked into the definition of palindrome. And then we have this formula for writing down the palindromes. Number of palindromes of length r is going to be n raised to r upon 2 when r is an even number. And number of palindromes of length r is equal to n raised to r plus 1 upon 2 when r is an odd number. Depending upon the length of the palindrome, we will choose these formulas. If r is an even number, then what we do is we will fill the first half blanks. If r is an odd number, then what we do is we will fill the first r plus 1 upon 2 blanks. Those things can be done in n raised to r by 2 ways or n raised to r plus 1 upon 2 ways. Next, we have these circular permutations. So number of permutations of n distinct objects taken all at a time is equal to n minus 1 factorial, or number of circular permutations is equal to n minus 1 factorial. So in this circular permutation, there is an exception. So in case of garland of flowers or chain of beads, we have to treat clockwise and anti-clockwise permutations as a single permutation. Therefore, number of permutations here is going to be n minus 1 factorial upon 2. So why we have to divide it by 2 means we are considering both clockwise and anti-clockwise arrangements as a single arrangement. If I want to interchange these two, then I have to make rearrangements. If I want to interchange these two people, then I have to make a rearrangement. If I want to interchange these two beats, I should not remove these beats. I can just rotate the chain. If I just rotate the chain, then it will give a rearrangement. So therefore clockwise and anti-clockwise both are treated as a single arrangement. Next we have permutations with constraints. So out of n objects, if p objects are alike, then the number of permutations is going to be n factorial upon p factorial. If out of n objects, p objects are of one kind, q objects are of second kind, and r objects are of third kind, then number of permutations is going to be n factorial upon p factorial times q factorial times r factorial. Next we have combinations. Number of combinations of n distinct objects taken r at a time is in general denoted by n choose r or NCR. You have to read it as n choose r. So this theorem tells us how many combinations we can have. Number of combinations of n distinct objects taken r at a time is npr upon r factorial. That is, n choose r is equal to npr upon r factorial, which is same as n factorial upon n minus r factorial times r factorial. Therefore, n choose r is equal to n factorial upon n minus r factorial times r factorial. Whereas npr is equal to n factorial upon n minus r factorial, and n choose r is equal to n factorial upon n minus r factorial times r factorial. So in general, NCR or n choose r is equal to n times n minus 1 times so on up to n minus r plus 1 upon r times r minus 1 times so on up to 2 times 1. So in the numerator you will have r terms, and in the denominator you will have r terms. But in the numerator it starts with n. In the denominator it starts with r. Number of subsets of S of length r or with r elements is going to be n choose r. Number of subsets with r elements is going to be n choose r, where n stands for number of elements of the set. If a set has n elements, then the number of subsets with r elements is going to be n choose r. Next we have this interesting corollary. N choose r is equal to n choose n minus r. Or we have this interesting theorem, n choose r is same as n choose n minus r. So n choose r means you are selecting r people from n people. Selecting r people out of n people is same as removing n minus r people from n people. So if in a class of 70 people, if I want to select 60 people, I can select 60 people, or else what I can do is I can remove 10 people. So if I remove 10 people also, then also I will get 60 people. So n choose r is same as n choose n minus r. So if you substitute r is equal to n, then you will have this result. N choose n is same as n choose 0, which is equal to 1. Number of ways of selecting n people from n people is going to be 1. Number of ways of selecting no people from n people is also going to be 1. Next we have these grouping theorems. So n and m are two distinct integers or positive integers. And the number of ways of dividing n plus m distinct objects into two groups containing n objects and m objects is going to be n plus m factorial upon n factorial times m factorial. I repeat, number of ways of dividing n plus m distinct things into two groups containing n things and m things is going to be n plus m factorial upon n factorial times m factorial. And then we have this generalization. Number of ways of dividing n plus m plus p distinct things into three groups containing n objects, m objects and p objects is going to be n plus m plus p factorial upon n factorial times m factorial times p factorial. So these results are applicable only if n and m are distinct. Here n should be different from m and m should be different from p. If all these three are distinct, then only we can apply these results. So if you want, you can see it using this example. Suppose I have these 6 objects, 1, 2, 3, 4, 5, 6. The number of ways of dividing these 6 objects into 2 groups containing 2 elements and 4 elements is going to be 15. Or you have this formula, n plus m factorial upon n factorial times m factorial. So here I can take n is equal to 2 and m is equal to 4. So the answer is 2 plus 4, which is 6 factorial upon 2 factorial times 4 factorial, which is equal to 6 times 5 upon 2, which is equal to 15. So there are 15 ways in which you can divide these 6 objects into 2 groups containing 2 objects and 4 objects. So if you want to apply the same result here, so here also I have to divide these 6 objects into 2 groups containing 3 objects each. If I use this same formula, n plus m factorial upon n factorial times n factorial. So here if I use the same formula, then I will have 6 factorial upon 3 factorial times 3 factorial, which is equal to 6 times 5 times 4 upon 3 factorial, which is equal to 20. So there are 20 ways in which you can divide these 6 objects into 2 groups containing 3 objects each. And these are the 20 ways. But actually if you observe, this arrangement is same as this one, or this division is same as this division. And similarly this division is same as this division. So we are repeating these 10 divisions one more time. So on the whole we are not getting 20 different divisions. We are getting only these 10 divisions. So what we have to do here is these two groups are same. So we have to divide it by 2 factorial. So we have this result. So the number of ways of dividing 2n distinct objects into 2 groups, each containing n elements, is going to be 2n factorial upon 2 factorial times n factorial times n factorial. So in general the result is 2n factorial upon n factorial times n factorial. But since those two groups are same, we have to divide it by 2 factorial. So which gives 2n factorial upon 2 factorial times n factorial times n factorial. And then we can generalize this result. The generalization is here. So the number of ways of dividing mn distinct objects into n groups, each containing into m groups, each containing n objects, is going to be mn factorial upon n factorial times m factorial times n factorial raised to m. The number of ways of dividing mn distinct objects into m groups, each containing n objects, is going to be mn factorial upon m factorial times n factorial raised to m. These are the total number of ways in which you can divide mn distinct objects into m groups. And next we have this corollary. The number of ways of distributing mn distinct objects among m people equally is going to be mn factorial upon n factorial raised to m. So if I want to distribute, then what I have to do is first I have to divide. After dividing, I have to distribute. So dividing can be done in these ways. Distributing can be done in m factorial ways. Distribution can be done in m factorial ways. So these are the number of ways of dividing. So if I want to distribute, first I have to divide and then distribute. Dividing can be done in these ways. Distribution can be done in m factorial ways. So if I multiply these two, then I will get this result. Mn factorial upon n factorial raised to m. These are the total number of ways in which I can distribute mn distinct things among m people equally. So these are the results that we have seen in the last class. Before going into the results related to combinations, there are 3 more problems that I have left out in the previous lecture. First, let us solve these 3 problems and then we can look into the results related to combinations. And this is our first problem. There are m points in a plane, out of which p points are collinear. and no three of these points are collinear unless those three are from those P points. Then find the number of different straight lines that can be formed using distinct lines or distinct points, joining distinct points. Find the number of different triangles that can be formed using these points. So first let us try to understand the question. So there are m distinct points in a plane. Out of those m distinct points, there are p points which are collinear. So 1, 2, 3, so on up to p. These are my p points which are collinear. And there are remaining points are not collinear. So remaining points are like this, scattered. And the other information that they have given is no three of these points are collinear. So if I join two points, then I will get I will get a line segment which passes through those 2 points, and it will not touch any other point. If I join these 2 points, then I will get a straight line which pass through these 2 points only. It will not pass through any other point unless those 3 points are from these P points. So if I join these 2 lines, these 2 points, if I join these 2 points with a straight line, it will pass through all the points. If I join these 2 points, second point and third point, then it will pass through all these P points. So this is the information that they have given. There are m points in a plane. Out of those m points, P points are collinear, and the remaining are not collinear. Now we have to find how many different lines that can be formed using 2 points. So any 2 points, joining any 2 points, we can have one straight line. So let us answer the first question. 2 distinct points gives a straight line. So in order to form a straight line, I have to find 2 distinct points. That means I have to select 2 points from these m points. In order to form a straight line, I have to select 2 points from these m points. This can be done in m choose 2 ways. But here this is not our correct answer, because these P points are collinear. If I choose my points 1 and 2, then what happens? It will form a straight line. That passes through all these P points. If I choose 2 and 3, it will also form a straight line, but those 2 straight lines are same. So if I choose any 2 points from these P points, I will get the same straight line. I repeat, if I choose any 2 points from these P points, then I am going to get the same straight line. So I am counting those same straight line, P choose 2 times more. So any 2 points from those P points gives the same straight line. But I have to count how many distinct straight lines that I can form, or how many different straight lines that I can form. So here I am counting same straight line many times. So I have to remove those repetitions. So we are counting P choose 2 straight lines as a single straight line. We are counting P choose 2 straight lines or we are counting single straight line p choose 2 times. We are counting single straight line p choose 2 times. So we have to discard that one. So total number of lines is equal to m choose 2 minus p choose 2. So m choose 2 is the total number of lines that we can form, and p choose 2 are the lines which we are counting repeatedly. But what happens here is, if I discard this p choose 2, then I am going to miss this straight line passing through all these p points. I am going to discard this straight line which passes through all these p points. Now we have to count that straight line also. So number of straight lines is going to be m choose 2 minus p choose 2 plus 1. Any 2 points gives me a straight line. But here we have p points which are collinear. All these p collinear points give rise to a same straight line. But I have to count distinct straight lines. So we are counting the same straight line p choose 2 times. So we have to eliminate those repetitions. So those repetitions can be eliminated by removing p choose 2. If I remove p choose 2, what happens is I am discarding the line passing through those p points. Therefore, the complete answer is m choose 2 minus p choose 2 plus 1. Now let us answer the second question. Number of triangles. Number of triangles. In order to form a triangle, we have to select 3 points. 3 non-collinear points gives a triangle. So if I select 3 non-collinear points, then it will give me a straight line. So this implies number of triangles is equal to m choose 3. So I have to select 3 distinct points from m distinct points. This can be done in m choose 3 ways. But here unfortunately we have p points which are collinear. If I select any 3 points from these p points, then I am not going to get a triangle because these 3 points are collinear. Therefore, I have to discard these selections. These selections means I should not select 3 points from these p points. So the total number of selections is going to be m choose 3, out of which I have to discard those p choose 3 ways or p choose 3 selections. 3 points from p collinear points will not give a triangle. Therefore, total number of triangles is equal to m choose 3 minus p choose 3. M choose 3 minus p choose 3. So here we are not adding plus 1 because all those p points form a straight line but not a triangle. So I request the students to spend some time on this problem and try to understand the concept. Next, we have this problem. A teacher wants to go take 10 students to a park, but he can take only 3 students at a time, and he is not supposed to repeat the combination. Find the number of ways in which a particular student can go to the park and a teacher can go to the park. So try to understand the problem. There is one teacher and 10 students. One teacher and 10 students. So for the time being, you assume that teacher has a car which has 4 seats and teacher occupies the driving position, and he can take 3 more students to the nearby park. So in how many ways he can go to the park? That is the question. And there is one more thing. So in how many ways a particular student can go to the park? Suppose you are there in those 10 students. So now in how many ways you can go to the park? The teacher can take only 3 students, and each time when he goes to the park he will not repeat the combination. So the number of ways that you can go to this park is number of ways each student can go 9 choose 2. So why we have 9 choose 2 means after removing a particular student, the total number of students is going to be 9, and teacher is fixed and you are fixed to go to the park. You have to select 2 more people. You can select those 2 more people from 9 people in 9 choose 2 ways. Next, the number of ways in which teacher can go is equal to is equal to 10 choose 3. So why that teacher can choose 10, I mean teacher has these many options means teacher is fixed, students are not fixed. So if he wants to go to the park, he have to select 3 students out of 10 students. So this can be done in 10 choose 3 ways. If a particular student wants to go to the park, then what happens is teacher is fixed, that particular student is fixed, and 2 more people should be taken to the park. So those 2 more people can be taken to the park in 9 choose 2 ways. So student can go to the park in 9 choose 2 ways, and teacher can go to the park in 10 choose 3 ways. Okay. Let us look into this interesting problem. A double-decker bus has 8 seats in the lower deck and 10 seats in the upper deck. So let us write down that information. So we have a double-decker bus. So time being, assume that this is your double-decker bus, and this is your lower deck, and this is your upper deck. And in the lower deck, the capacity is 8 people or 8 passengers. And in the upper deck, the capacity is 10 people. Now there are 18 people waiting to board the bus. In those 18 people, there are 3 children who wants to sit in the upper deck. And there are 4 elderly person, they cannot climb to the upper deck. Now find the number of ways of arranging these 18 people in the bus. So read the question carefully and then you can solve the problem. So we have a double-decker bus which has 8 seats in the lower deck and 10 seats in the upper deck. And there are 18 passengers or 18 people. So we have to arrange these 18 people in this double-decker bus. If there are no restrictions, I can arrange these 18 people in these 18 seats in 18 factorial ways. But here there are some restrictions. The restrictions are, there are 3 children, they want to sit in the upper deck. And there are 4 elderly person, they cannot climb to the upper deck. So those 4 people, the 4 elderly person should be accommodated in the lower deck, and those 3 children should be accommodated in the upper deck. So the first thing that you have to do is, you have to send these 3 people, 3 children to the upper deck and 4 people to the lower deck. First send the 3 children to the upper deck. And 4 elderly persons to the lower deck. After sending 3 children to the upper deck and 4 elderly person to the lower deck, the upper deck can still accommodate 7 people and lower deck can still accommodate 4 more people. So the remaining people are 18 minus 3 minus 4, which is equal to 18 minus 7, which is 11. So we have 11 more people which are waiting, who are waiting. Now out of these 11 people, what we have to do is we have to send 7 people to the upper deck and 4 people to the lower deck. So our task is to arrange these 18 people in this bus. So this task can be divided into two works, namely W1. W1 is to send 10 people to upper deck and 8 people to lower deck. And W2 is to arrange these people. Okay. Now, in order to send 10 people to the upper deck, we have already sent 3 people. Now we have to send 7 more people to the upper deck and 4 more people to the lower deck. That is 7 more to upper deck and 4 more to lower deck. In how many ways you can send 7 people to the upper deck and 4 people to the lower deck? That is your first question. So we have 11 people here. So we have to distribute these 11 people into these 2 decks. So I cannot send all the 11 people to the upper deck and I cannot send all the 11 people to the lower deck. I can send only 7 people to the upper deck and I can send only 4 people to the lower deck. So if I select 7 people from 11 people, those 7 people will go to the upper deck and the remaining 4 people will go to the lower deck. So this can be done in number of ways of doing W1 is equal to 11 choose 7 or 11 choose 4, both are same because n choose r is same as n choose n minus r. If I select 7 people, these 7 people will go to the upper deck and the remaining 4 people will automatically go to the lower deck. Now W2 is to arrange those people. In this W2 also we have two things, in the lower deck, in the upper deck. In the upper deck we have 10 people, in the lower deck we have 8 people. So in the lower deck we can arrange them in 8 factorial ways. In the upper deck we can arrange them in 8 factorial ways. So the total number of ways of seating is equal to total number of ways of seating is equal to 11 choose 7 times 8 factorial times 10 factorial. These are the total number of ways in which we can arrange these 18 people into this double decker bus, where we have the constraint that 3 children wants to climb upper deck or 3 children wants to sit in the upper deck and 4 elderly person wants to sit in the lower deck. The total number of arrangements is this one. So this is the problem where we are using the concepts of combinations and we are using the concept of permutation. So we are using the concept of combination means we are selecting 7 people out of 11 people. This can be done in 11 choose 7. So first we distribute the people into upper deck and lower deck. So first we are grouping the people. So this can be done in 11 choose 7 or 11 choose 4 ways. So after grouping, then what we do is we are arranging. First we are sending 10 people to the upper deck. Those 10 people will be standing and those 8 people will be standing in the lower deck. After that we will arrange those 10 people in the upper deck in 10 factorial ways and we can arrange those 8 people in the lower deck in 8 factorial ways. So the number of ways of seating is equal to first distribution and then arrangement. Distribution can be done in 11 choose 7 ways and arrangement can be done in 8 factorial times 10 factorial ways. So this is your answer. Now let us look into few theorems related to combinations. So before looking into the theorems related to combinations, we have these results. If n choose r is equal to n, I mean n choose r is equal to n choose n minus r. So we have already proved this theorem. And what about the converse? If n choose r is equal to n choose s, can we say that r is equal to s, or r is equal to, or s is equal to n minus r? So what about the converse? If r is equal to s, there is no problem. If r is equal to s, then it is an obvious question. I mean, it is an obvious thing. If r is not equal to s, can we say that s is equal to n minus r? So we have already proved this theorem. N choose r is same as n choose n minus r. What about the converse? What about the converse in the sense, if n choose r is equal to n choose s, then can I say that s is equal to n minus r? Can I say that s is equal to n minus r? That is the question. So here luckily the converse is also true. So we can prove that theorem, but before going into that theorem, we use this result. So if you use any result in a particular theorem, then that result is called as lemma. So here we have this lemma. Suppose a and b are positive real numbers and k is a positive integer, and a plus 1 times a plus 2 times so on up to a plus k is equal to b plus 1 times b plus 2 so on up to b plus k, then a is equal to b. The product of these consecutive numbers in the sense difference of these numbers is 1. The difference of any two successive numbers is 1. So if the product of these kind of numbers is equal to product of these kind of numbers, then a must be equal to b. So without delaying much, let us try to prove this theorem. Proof. So without loss of generality, let a is not equal to b. So if I assume that a is not equal to b, then what I can have is I will get a contradiction. So why I am getting a contradiction means because here my assumption is wrong. So let us see whether we will hit a contradiction or not. So without loss of generality, let us assume that a is not equal to b. So a is not equal to b means a is greater than b, or b is greater than a. So for the time being, let me assume that a is greater than b. So this implies a plus 1 is greater than b plus 1, and a plus 2 is greater than b plus 2. Or more generally, we can write a plus I is greater than b plus I for all I is equal to 1 to k. Now I can multiply all these inequalities. This implies a plus 1 times a plus 2 so on up to a plus k is greater than b plus 1 times b plus 2 so on up to b plus k. So after multiplication also the inequality will not change. Why the inequality will not change means here both are positive numbers. A plus I and b plus I both are positive numbers, because a is a positive number, b is a positive number, and I is a positive integer. Therefore a plus I and b plus I both are positive integers, positive numbers. So multiplying these multiplying these things will not change the inequality. So we have this inequality, but it is a contradiction. Why it is a contradiction means it is given that a plus 1 times a plus 2 so on up to a plus k is equal to b plus 1 times b plus 2 so on up to b plus k. Therefore our assumption is wrong. So what is our assumption? A is not equal to b is wrong. So this implies a is equal to b. So no need to worry about the result. So we are just using this result in the next theorem. So if the product of these consecutive numbers, not consecutive numbers, product of these numbers, the difference between any two consecutive numbers is 1. The product on the left side is equal to product on the right side, then a must be equal to b. So we use that result lemma, or we use that lemma in proving this theorem. So let us try to prove this theorem. So what is given here? Given n choose r is same as n choose s. What needs to be proved here? Either n is equal, r is equal to s, or n is equal to r plus s. Okay, so let us start with what they have given. N choose r is same as n choose s. Now we have to prove this, either r is equal to s or n is equal to r plus s. R is equal to s is an obvious thing, so we will not prove that one. So if r is equal to s, then there is nothing to prove. Okay, so let us assume r is not equal to s. Let r is not equal to s means either r is less than s or r is greater than s. So for the time being, you can assume that r is less than s. Now n factorial upon n minus r factorial times r factorial is same as n factorial upon n minus s factorial times s factorial. So n factorials you can cancel out. So you will have n minus r factorial times r factorial is same as n minus s factorial times s factorial. So we are assuming that r is less than s. This implies minus r is greater than minus s, or n minus r is greater than n minus s. So out of this n minus r and n minus s, I have to expand n minus r. If I start expanding n minus r, then I will hit n minus s. Okay, and then coming to r and s, I can expand s factorial. Okay, so let me expand these things. So let me do it in the fresh page. Okay, so n minus r factorial, I can write it as n minus r times n minus r minus 1 and so on, n minus s minus 1 or plus 1 times n minus s factorial times r factorial is equal to n minus s factorial times s factorial. I can expand and write it as s times s minus 1 times so on up to r plus 1 times r factorial. So we can expand up to this one. When we start expanding s factorial, we will hit r. When we start expanding n minus r factorial, we will hit n minus s. So we have this result. So we can cancel out n minus s factorials, and then we'll have this result, n minus r times n minus r plus 1, sorry, n minus r minus 1, so on up to n minus s plus 1 is equal to s times s minus 1, so on up to r plus 1. So we have this result, a plus 1 times a plus 2, so on up to a plus k is equal to b plus 1 times b plus 2, so on up to b plus k, implies a is equal to b. So we have proved this result. Now we can apply this result here and we can prove the theorem. So let us see how we can apply this theorem, result. So let a is equal to n minus s plus 1 and b is equal to r plus 1 and s is equal to, k is equal to s minus r. So you apply these things, or you assume a is equal to this one, b is equal to this one, and c is equal to this one, and apply here. Then you will get the previous result. So this implies a is equal to b, or n minus s plus 1 is equal to r plus 1. This implies n is equal to r plus s. So don't get worried about the proof. You have to just remember the statement of the theorem. And the statement of the theorem is like this. If n choose r is equal to n choose s, then we have two choices. The first one is obvious one, that is r is equal to s, and the second one is n is equal to r plus s. In order to prove this theorem, we have this lemma. So don't give much importance to this lemma and the proof of this theorem. You have to just remember the statement of the theorem. And the statement of the theorem is if n choose r is equal to n choose s, then n is equal to r plus s. And the other one is r is equal to s. R is equal to s is obvious thing. All that you have to prove is n is equal to r plus s. Okay, let us move on to the next result. We have this interesting result. It is n choose r minus 1 plus n choose r is equal to n plus 1 choose r. So before going into the proof of this theorem, before going into the proof of this result, let me recall a familiar result to you in permutations. In permutations, we have looked into this one. NPR is equal to n minus 1 PR plus R times n minus 1 PR minus 1. So here NPR stands for number of permutations of n distinct objects taken R at a time, and here R times n minus 1 PR minus 1 stands for number of permutations of n distinct objects taken R at a time, which always includes a particular object. And n minus 1 PR stands for number of permutations which does not include a particular object. Suppose I have n objects, 1, 2, so on up to n. So let me take those objects like this. So if I have a particular object like this, if I have a special object, number of permutations of these n objects taken R at a time is NPR. Number of permutations without this object means I will have n minus 1 objects. Number of permutations is going to be n minus 1 PR plus which contains this object is going to be R times n minus 1 PR minus 1. So we have seen this result. Now we have to mimic this result in combinations. So how we will mimic this result in combinations, we will see. Okay. Proof. Let us have n plus 1 objects. N plus 1 objects, 1, 2, so on up to n, and we have a special object like this. So these are my n plus 1 distinct objects. Now out of these n plus 1 distinct objects, I have to select R. Number of ways of selecting is equal to number of ways of selecting R things out of n plus 1 is n plus 1 choose R. This is my RHS. Now I can choose R things out of n plus 1 things in n plus 1 choose R ways. Now here I have these n plus 1 objects. Now in how many combinations my special object will be there, and in how many combinations my special object will not be there? These are the two questions. Next, number of combinations which include the special object is, I have already included this object. I am supposed to collect R objects out of this n plus 1. I have already collected this object. So now all that I have to do is I have to select R minus 1 objects from the remaining n objects. I repeat, if I already include this special object, I have to select R minus 1 objects from the remaining n minus 1 objects, or from the remaining n objects. So the total I have n plus 1 objects. The remaining objects are going to be n. So I have to select R minus 1 objects out of these n objects. This I can do it in n choose R minus 1. These are the total number of ways of selecting R objects in which this special object is always there. Now, number of combinations without that object. Without that object means I have to select R objects out of these n plus 1 objects. But without that object means I have to select R objects out of these n objects. So number of combinations without that object is going to be n choose r. Now total number of combinations is equal to total, that is n plus 1 choose r is equal to n choose r minus 1 plus n choose r. So this is our result. Let me explain the result for you. We have n plus 1 distinct objects, and these are my n plus 1 distinct objects. I have to select r objects out of these n plus 1 objects. I can select r objects out of these n plus 1 objects in r plus 1 choose r objects. N plus 1 choose r ways. I can select r objects out of these n plus 1 objects in n plus 1 choose r ways. This is my RHS. Now, the number of combinations in which this object is always there. I have already selected this object. Now, how many more objects I have to select? I have to select r minus 1 more objects from these remaining n objects. The remaining objects are n, and I have to select r minus 1 objects. So this can be done in n choose r minus 1. These are the total number of combinations which always includes this particular object. Now, number of combinations without this object. Without this object means I have these n objects and I have to select r objects. So this can be done in n choose r ways. The total number of combinations is equal to number of combinations in which this object is there plus number of combinations in which this object is not there. The total number of combinations is going to be n plus 1 choose r is equal to n choose r minus 1 plus n choose r. So if you are not satisfied with the proof, you can just expand n choose r minus 1 and n choose r, and then you can give a proof. But I am interested in this proof, and I encourage the students to give the proof in this way only. Next, we have this interesting corollary of the previous result. Okay, so the corollary is like this: n choose r minus 2 plus 2 times n choose r minus 1 plus n choose r is equal to n plus 2 choose r. I repeat, n choose r minus 2 plus 2 times n choose r minus 1 plus n choose r is equal to n plus 2 choose r. So those who are good in calculation, they can expand these things and they can give a proof. But without expanding all these things, we can give a combinatorial proof. And the proof is like this. So in RHS, we have n plus 2 choose r. That means we are selecting r objects out of these n plus 2 objects. So let me write those n plus 2 objects. So we have these n plus 2 objects, 1, 2, so on up to n, and we have 2 objects. So on the whole, we have n plus 2 objects, and these are my n objects. So all these objects are distinct. Now I have to select r objects out of these n plus 2 objects. Selecting r objects out of these n plus 2 objects can be done in n plus 2 choose r ways. Now, number of combinations in which these two objects are not there. So here n choose r minus 2. This gives number of combinations without those two objects. Okay. Now, n choose r minus 1. So let us look into this one, n choose r minus 1. N choose r minus 1 means I am selecting r minus 1 objects out of these n objects. I repeat, n choose r minus 1 stands for selecting r minus 1 objects out of these n objects. But my target is to select r objects. I am selecting only r minus 1 objects. So I have to select one more object. I can select one more object from these two. I can select one more object from these two in 2 choose 1 ways. I can select one object from these two in 2 choose 1 ways, which is 2 choose 1 times this one. 2 choose 1 is nothing but 2. So 2 times n choose r minus 1 stands for number of combinations in which exactly one special object is there, one special thing is there. 2 times n choose r minus 1 stands for number of combinations in which exactly one object is there in the combination. Now n choose r minus 1, n choose r minus 2 stands for number of combinations in which those two objects are there. 2 times n choose r minus 1 stands for number of combinations in which exactly one object is there. Now, how many combinations are there without containing these two? So without containing these two means I have to select r objects out of those n objects. So n choose r stands for number of combinations in which those special objects are not there. N choose r stands for number of combinations in which those objects are not there. 2 times n choose r minus 1 stands for number of combinations in which exactly one special object is there. And n choose r minus 2 stands for number of combinations in which exactly, those two objects are there. N choose r minus 2 stands for number of combinations in which those two special objects are there. So if I add all these things, then I will get the number of combinations in which, the number of ways in which I can select r objects out of these n plus 2 objects. If I add all these three, then what I will get is the number of combinations of these n plus 2 objects in which, number of ways of selecting r objects out of these n plus 2 objects. I repeat, if I add all these three quantities, then what I am going to get is the number of ways of selecting r objects out of these n plus 2 objects. So this is the proof of this theorem, or this is the proof of this corollary. Coming to the next theorem, the statement of the theorem is like this. If p things are alike of one kind and q things are alike of another kind and r things are alike of another kind, and the number of ways of selecting one or more objects is p plus 1 times q plus 1 times r plus 1 times minus 1. Sorry, the number of ways of selecting is p plus 1 times q plus 1 times r plus 1 minus 1. So try to understand the statement of the theorem. There are p things which are alike and there are q things which are alike and there are r things which are alike. Now you have to select one or more objects out of these three. So the number of ways of selecting is equal to p plus 1 times q plus 1 times r plus 1 minus 1. So let me explain the statement of the theorem with this picture. So I have p pencils. And I have q erasers and I have r pens. All these p pencils are alike and all these q erasers are alike and all these r pens are alike. Now a little boy is there. So he is moving towards these objects. Now in how many ways he can select these objects? The question is, in how many ways he can select these three objects? He can select these objects. He can select either 0 pencils or 1 pencil or 2 pencils, so on up to p pencils. So number of ways of selecting pencils is going to be p plus 1. Similarly, he can select 0 erasers or 1 eraser or 2 erasers, so on up to q erasers. Number of ways of selecting erasers is going to be q plus 1. And he can select 0 pens or 1 pen or 2 pens, so on up to r pens. So number of ways of selecting pens is going to be r plus 1. Now the total number of ways of selecting these objects is going to be p plus 1 times q plus 1 times r plus 1. But there is one combination where 0, 0, 0 is there. If we select 0 here, 0 here and 0 here, then he is not going to select anything. That is not allowed. So we have to remove 1. Therefore the result is p plus 1 times q plus 1 times r plus 1 minus 1. So you can take this as the proof. Okay, so I am explaining the proof of this theorem using this picture. Suppose you have p pencils and q erasers and r pens, and there is a little boy. He wants to grab these objects. In how many ways he can grab these objects? That is the question. He can grab these pencils in any of these ways. He can take 0 pencils or 1 pencil or p pencils. So the number of ways of selecting pencils is equal to p plus 1. And similarly the number of ways of selecting erasers is equal to q plus 1. And similarly the number of ways of selecting pens is equal to r plus 1. Therefore the number of ways of selecting any of these objects is equal to p plus 1 times q plus 1 times r plus 1. That is without any restriction. But we have a restriction in the theorem. The restriction is we have to select one or more objects. So if I select 0 pencils and 0 erasers and 0 pens, it is going to be an array. We are not selecting any object. So that is not a required thing. So we have to remove that combination. The total number of ways of selecting is equal to p plus 1 times q plus 1 times r plus 1. But we are not including 0, 0, 0. Not including 0, 0, 0. We are not including this combination. So minus 1. So total is equal to p plus 1 times q plus 1 times r plus 1 minus 1. You can just take this one as a proof. Let me look into the statement of the theorem one more time. We have p things which are alike and q things which are alike and r things which are alike. Then the number of ways of selecting one or more objects is going to be p plus 1 times q plus 1 times r plus 1 minus 1. And the proof is like this. P pencils, q erasers and r pens. The number of ways of selecting any of these objects. So here we have a little boy, and the number of ways of selecting any of these objects by this boy is going to be p. Selecting pencils is p plus 1, selecting erasers is q plus 1, selecting pens is r plus 1. So total number of ways of selecting is equal to p plus 1 times q plus 1 times r plus 1. But we are not allowed to select 0, 0, 0. So we have to remove this combination. So this is a unique combination. So by removing this one, we will get the required combinations. That is p plus 1 times q plus 1 times r plus 1 minus 1. Now we have this corollary. The statement of this corollary is like this. The number of ways of selecting one or more objects from n distinct objects is going to be 2 raised to n minus 1. This is a corollary of the previous theorem. So in the previous theorem we have p things alike, q things alike and r things alike. But here all the objects are distinct. Suppose let us assume that we have only 3 objects. We assume that there are 3 distinct objects. So p is equal to 1, q is equal to 1 and r is equal to 1. Then if you apply the previous result, then what you will have is 1 plus 1 times 1 plus 1 times 1 plus 1 minus 1, which is 2 raised to 3 minus 1. If you have 3 distinct objects, then it is going to be 2 raised to 3 minus 1. If you have 4 distinct objects, then it is going to be 2 raised to 4 minus 1. If you have n distinct objects, then it is going to be 2 raised to n minus 1. So let us give the proof of this one. If we have 3 distinct objects, then p is equal to 1, q is equal to 1 and r is equal to 1. This implies number of ways is equal to 1 plus 1 times 1 plus 1 times 1 plus 1 minus 1, which is equal to 2 raised to 3 minus 1. If we have n objects, then we have 2 raised to n minus 1. These are the total number of ways in which you can select one or more objects. So minus 1 we are having because we are supposed to select one or more objects. If you are allowed to select 0 objects, then the result is going to be 2 raised to 1. So in the previous theorem also, if you are allowed to select no objects, then the result is going to be p plus 1 times q plus 1 times r plus 1. We will not have minus 1. So here also, if you are allowed to select 0 objects, then the result is going to be 2 raised to n. But here you are not supposed to select 0 objects. The number of ways of selecting one or more objects is going to be 2 raised to n minus 1. We have an application of the previous theorem or previous corollary. The application is like this. If P1, P2 up to Pk are distinct primes and alpha 1, alpha 2 up to alpha k are positive integers, and the number of divisors of n, where n is equal to P1 raised to alpha 1 times P2 raised to alpha 2 so on up to Pk raised to alpha k, is alpha 1 plus 1 times alpha 2 plus 1 so on up to alpha k plus 1, which includes 1 and itself. The number of divisors of n is going to be alpha 1 plus 1 times alpha 2 plus 1 so on up to alpha k plus 1, where n is equal to P1 raised to alpha 1, P2 raised to alpha 2 so on up to Pk raised to alpha k. Let us try to understand this result using an example. After understanding the result, we can give the proof easily. So let us try to find out the divisors of 72. So 72 we can write it as 2 cubed times 3 square. 2 cubed is 8, 8 times 9. 72 is 8 times 9, 8 you can write it as 2 cubed and 9 you can write it as 3 square. So let us try to write down the divisors of 72. So any divisor of 72 will be of the form 2 raised to lambda and times 3 raised to beta. Any divisor of 72 will be of this form. So it will not be of the form 5 power something, or it will not be of the form 7 power something. So any power of 5 will not be a divisor of 72, or any power of 7 will not be a divisor of 72. All the divisors of 72 will be of this form, 2 raised to lambda and 3 raised to beta. Okay, so 72 you can write it as 2 cubed times 3 square. Okay, let us write down the divisors of 72. So 172, this is 1, 2 and 36, 3 and 24, 4 and 18, 6 and 12, 8 and 9. And these are the 12 different divisors of 72. Now how can we get these 12 different divisors? That is the question. So any divisor will be of the form 2 raised to lambda and 3 raised to beta. So if I want to select a divisor, I can select some 2's and I can select some 3's. How many 2's I can select and how many 3's I can select, that is the question. So here number of 2's is going to be 3 and number of 3's is going to be 2. So I can select 2's in 4 ways. So 2 power 0 is a divisor, 2 power 1 is a divisor, 2 power 2 is a divisor and 2 cube is a divisor. 3 raised to 0, 3 raised to 1 and 3 square. All these 3 are divisors. So all these 4 are divisors and all these 3 are divisors, or any product of these 2 is also a divisor. So we can do like this. There are p things which are alike, or there are 3 things which are alike, 3 2's, and there are 2 things which are alike. There are these 2. So you can take p is equal to 3 and q is equal to 2. There are p things which are alike and there are q things which are alike. The number of ways of selecting any number of objects is going to be p plus 1 times q plus 1. which is going to be 3 plus 1 times 2 plus 1, which is going to be 4 times 3, which is going to be 12. There are 12 different ways of selecting these things, or there are 12 different devices. So here we have 3 identical 2's and there are 2 identical 3's. That means there are 3 objects of one kind and there are 2 objects of another kind. The number of ways of selecting any number of objects is going to be p plus 1 times q plus 1. So if you apply this, if you understand this one, then we can give the proof of this theorem easily. Any divisor of n will be of the form p1 power lambda 1 times p2 power lambda 2 so on up to pk power lambda k, where lambda I can vary from 0 to alpha I. That is, lambda I have alpha 1, alpha I plus 1 choices. So number of divisors is equal to alpha 1 plus 1 times alpha 2 plus 1 so on up to alpha k plus 1, because I can select any number of objects. I can select any number of objects. Now if I want to have proper divisors in the sense without including 1 and itself. So without including 1 and itself means minus 2. The number of proper divisors of n is going to be alpha 1 plus 1 times alpha 2 plus 1 so on up to alpha k plus 1 minus 2, because we are excluding 1 and n itself. Therefore the number of proper divisors is this one, and the number of divisors is this one. Number of divisors is this formula, and the number of proper divisors means this one. Proper divisors means we have to exclude 1 and itself. If I ask you to write down what are the divisors of 12, the divisors of 12 are 1, 2, 3, 4, 6 and 12. But proper divisors are 2, 3, 4 and 6. 1 and 12 are not called as proper divisors. Okay. Next we have a small definition. The definition is like this. Exponent of a prime in n factorial. So exponent of a prime in n factorial means p power k divides n factorial, but p power k plus 1 does not divide n factorial. So in order to find that exponent, we have this formula. Step of n upon p plus step of n upon p square plus step of n upon p cube plus so on. So by using this formula, we can find out the exponent of a prime. And the problems related to these results will be discussed in the next lecture.